nailed it. And we'll go back into the ray tracing because we've got a couple more examples to look at from yesterday. So we looked at one. Let me just quick go over to that. The example that we looked at yesterday was the case of a spherical concave mirror. So one that the center of it goes away from us. Looking at an object that is outside its focal point. And we saw that this kind of mirror converges the rays. So another name for this kind of mirror is often a converging mirror because the rays that hit it tend to converge into a single point. Now, if all of these rays were coming in, I'm going to bring up show another image of this. Just use the point that we want. If we had this kind of mirror and a whole bunch of points coming from a very distant object, what we can say about those light rays is that they would come in parallel to one another. So I'll draw a second one in here. And all of those rays, move you guys, all of those rays are going to be reflected so that they go back through the focal point. That's what's meant by a focal point. This is useful in optical equipment because you can take something, and especially like a telescope, you can take something that's really, really distant. The rays coming from it have to be basically parallel as they are entering the circular part of the mirror, and then they all focus down to that one point. This is also why this kind of mirror could be used to take the sun's rays and focus it onto a very, very hot spot. Right? So this is called a converging mirror. And we saw that when things are closer to the mirror, we can actually use it to form an image of them as well. And so this object was a bit out of its focal point, and the rays from it all converged at a little bit beyond its focal point into a smaller inverted image. So we noted that that image form would be upside down and flipped left to right, so completely inverted. It would be demagnified, so it's smaller than the original. And it is a real image. And this is a topic that we'll come back to a lot. Real image means that the rays that are reflected from it do converge somewhere in actual space where the light rays are actually there and intersecting. And that means we could display this on a screen. So if we had the object out here on the left and a small screen here, then we could actually show that onto the screen and then we could see it. We could also see it with our naked eye looking into the mirror. If you haven't had a chance, do check out those those 4 short videos that I posted in the video section of chapter 11 of unit 11, because they actually demonstrate this really, really well with large mirrors. Okay, so that is one situation we're going to look at. Did anyone have any questions that you'd like to ask on that situation before we go on to the next? Okay, so the next situation we're going to look at is using the same kind of mirror, but now we're going to place the object inside the focal length. So let me that's weird. So our object now, you can see where the focal point is, and the object is inside it. And let's see what happens. Now the rules that we had are going to be applied to this mirror as well. We just have to apply them a little bit differently because of where this is. So those rules, again, at the top, we'll draw one ray from the top of the object that is parallel to the optical axis. and then that will be reflected through the focal point. So I'm going to do that first, and that was my red one. So I'll try and keep consistent color. So we're going to go to the top, make a parallel to the optical axis. It'll hit the mirror there, and then reflect back through that focal point. Okay, so there is ray 1. Ray 2, oh, I'll give you a moment to sketch this, sorry. I don't want to get too far ahead of you. Yeah. And remember, while you're sketching these in your notes, they don't have to be super, super precise, just show what we're doing. But then in the examples, when we actually do this for measurement in homeworks or well, we don't get the test, but in tests and situations, we could measure this very carefully and get good results, which I should be able to get using this program. Okay, so our second ray, we go from the top of the object through the focal point, and it's reflected to the optical axis. So this one's a little different because if we go directly through the focal point here, it doesn't hit the mirror at all. So instead what we do is we take that ray and imagine that it originates at the focal point and extend it to the mirror like this. I think that one was green. Right, so technically speaking, it's not going from the focal point. So I'm gonna do something with this. I'm gonna make that a dashed line. No, Ginny. And the only real part of the line then is going to be from the tip of that to the mirror. Cat. Yeah, you can go up there. Okay, and then the same rule applies though. Since it seemingly went through the focal point, it would be reflected parallel to the optical axis. Like that. And then this dashed line that I've got there doesn't actually exist. It's just there to mark the direction that we want. And our final ray that we drew was from the top of the object to the optical axis intersection with the mirror, and then reflected back at the same angle. I think I can make this. So, nope, didn't want to do that. So I'm going to go from the top of my object down to the point there where the mirror intersects with the optical axis. And then that one will reflect, since that's the flat part of the mirror, according to the optical axis, it will reflect downward at the same angle that it was incident at. So this is like a closest thing we have to a plane mirror in this scenario. Oops. So who can spot the issue that we're going to have with these three rays, the red, green, and blue coming off the top of our object?
Doesn't look like they'll ever meet.
Nope, they won't.
Except on the other side of the mirror.
Right. So this is like what we saw with the plane mirror. So these won't meet, but I'm going to take them and draw them at the same angle, the reflected ray, draw it back behind the mirror. So I'm going to take this one, put it like so, and I'm going to make those dashed so that we can see that these are not real rays. I'll take that one. That's going to give me too much, but I'm going to take it. Let's do this. Then I'm going to take the red one. And I got my angle a little bit off, or so I'm going to adjust just slightly, or one of my measurements a little bit off. So what I'm going to do is this. If I change that just slightly, it would probably work. This one, when extended, will go right through that same point. And that's pretty easy to do, to get off by just a little if one of your measurements is off a little bit. And I thought I was pretty careful, but. Okay, and where those three lines intersect is where this part of our object is going to be. So I'm going to copy and paste my object back here to illustrate that.
So since you had to make the arrow bigger, does that mean the object is also going to get bigger?
Right. Well, the object, no, the image is bigger.
Or, well,
So,
yeah.
yep. So we had some observations that I'm going to click and drag down here. Okay, so let's look at the similar kinds of things about this image. So namely, compared to the object, is the image upside down or right side up?
Right side.
Right side up. Spoiler, it would, if we flip this around, it would still be flipped left to right. Mirrors always do that. Is it bigger or smaller though? Obviously, this is the image here. So let's put a little note there. The image is quite a bit bigger. So this is actually magnified. Than the larger than the object. Okay, and then the last part is this real or is it virtual? Well, real images, the real image formed because we could put an actual physical screen where the light rays intersect and project the image onto that screen. This one we can't do that with. This one is behind the mirror and the mirror is solid. It doesn't actually allow the light to go through it. So that makes this a virtual image. So formed behind the mirror. We can't project it onto something. We can only see it when we look into the mirror because the lenses in our eyes take these diverging rays and converge them and show us where they would meet behind the mirror. This would be a way to use it sort of as a magnifier. Lenses typically work more easily for this. But this is illustrated really, really well. The difference between these two situations in particular, where we had an object outside the focal point and an object inside the focal point, but otherwise of the same kind of mirror. It's illustrated really, really well in the first couple of videos that I put up in that playlist with the older professor looked like, and he had a really nice big mirror, and we could see the images in it. So check those out for sure to see the differences and see what happens as an object moves from close to a mirror to far away from the mirror. You can see in the video what that image would look like. Any questions on this one? We got one more. Okay. And then, so the last one we're going to look at is going to be an object in reflecting from a convex mirror. So the convex mirror here, oops, wrong way. Convex mirror is still a spherical mirror, so it's part of a sphere. Put those down here. But this time, the near point is in the center, and then it's curving away from it. So that's like the backside of a spoon. I have listed the center of curvature again. This would be the center of the sphere that it's cut out of. And then the focal point is half the distance between the mirror and that center. It won't matter exactly really where our image is on this side. So I put it a little ways away, but it's just got to be somewhere to the left of the mirror. The rules for ray tracing this are the same as previous, but again, we have to adapt it to this situation. So our first one will come in from the top of our object, parallel to the optical axis, and strike the mirror. But now when they reflect, they can't actually go through the focal point because the focal point is behind the mirror. And so instead, it reflects as though it was going through. So I start, I'll have to zoom in to get this part. I start right at the center where the focal point is on the optical axis, and then make my line away. Right, so, and then I'll break this back out. So there's the actual part, and then just to show you how I determined that, I'm going to make this one dashed line because it's not really there. The second line we had, second ray, went from the top of the object through the focal point and then reflected parallel. Well, again, it can't actually go through the focal point, but we're going to draw it as though it is hitting the focal point, like that. And where it hits the mirror, we reflect it back parallel to the optical axis. So right there, back. And again, then this part behind the mirror gets shortened, and I'm going to put a dashed line back there. Okay, and our final one, from the top of the object to the optical axis intersection with the mirror, and then reflected back at the same angle that it's incident. Like so. And we have a bit of the same problem that we saw with the last mirror. These reflected rays, the red one here, the green one there, and the blue one there, are never going to meet in real space. So this means that this will not be a real image, but it does look like if I trace back their reflected rays, they should intersect somewhere behind the mirror. So I've actually already done that with the red one, right? I use that to draw it. The green one Although I put a dashed line through here, that was really just to help me figure out where the focal, or how to hit the focal point. So that's not the reflected ray. The reflected ray here is parallel, and I'll have to draw one back. So let me, I'm gonna make this maybe I'll just make it black just so that we can see it, because the green here is going to be the important one. So I'm gonna go from this point back because that's a reflection of the that is the reflected ray going backwards. And then I'm going to do the same thing with the blue. And again, let's see how close I am. Oh, that one turned out perfectly. So now where these meet, not the black one, because that was just to help me draw my incident ray, but the three reflected rays all meet at a point right there. So I'm going to take my object and put it there because that is the site of my image. Let's make that gray. Okay, we have the same sorts of questions then when we form that image. I'm going to go up and grab my question or my observations and then bring it back down. Okay, when we compare this to our object, right there, we can see, well, this image is is right side up. It will still be flipped left to right. We don't actually see that in this image, but just like all mirrors, it is flipped left to right. It is much, much smaller than our object. So that means it'll be demagnified. Is this a real or a virtual image? Could we project it?
Virtual, because we had to do a mirror.
Right. We had to go behind the mirror, so this means it's a virtual image, which is formed behind the mirror. We use these different types of mirrors in different cases. I had the makeup mirror down here yesterday. That's a good example of a concave mirror. And that one is usually used with the object, your face, within the focal point. So that means the image you see of your face is enlarged. It is flipped left to right, but it's upright. It's enlarged so you can see all of those tiny little faults that you want to hide. If we have an image outside of the focal point, it's useful for focusing the light rays together and making an image we could project on something. This one's used a lot in telescopes because it can take very distant objects, focus their light down to a small point, and then we can use a lens, and we'll deal with lenses later, to magnify that image. Does anyone think of a use where this might be useful? Because this object is quite a bit smaller, or the image is quite a bit smaller than the object. It seems to be closer to the mirror than the object is. The object is quite a bit farther from the mirror than the image. Where would we use something like this?
A car.
A car.
Or mirror.
Yep. You notice on the passenger side mirrors on the sides that it always say, caution, object and mirror is closer than they appear. That's because it looks so tiny. But the advantage of that is is, since our mirror there is curved, we can actually see a lot farther around. The angle is a lot farther. So we can see objects over here and down here, not just out through the middle. So that, I think, is illustrated pretty well in the videos as well, how you can see from a greater angle. We see these kind of mirrors in shops and things all the time. So they might be up in the corner of a shop, sort of a security window or a security mirror, because a person from the cash register could look at that and then see practically the whole store and keep an eye on things. So even though the image is quite a bit smaller and always will be here, it is upright, so that makes it easier to recognize, and that wide angle view is really useful as well. So that's the 3 different types of ray tracing you'll have to know for the mirrors. Does anyone have any questions you'd like to go over? We only have a few minutes left, and tomorrow we'll add some math to this. But for today, this is a good progress. But any questions? Okay, the first couple in the homework for this week, there are a couple of questions that ask you to ray trace find the solutions. These are the techniques you'd use for that. Measure them very, very carefully. Also, especially if you've got a circle drawer, compass sort of thing, use that to make your mirror, because if you make a mirror that isn't actually spherical, this won't work out as well. And then make some measurements for the distance of the object from the focal point or the mirror, and where the image is, you'll be able to use the scale that you set up to find the actual distance where the image would be formed. Tomorrow, there are also a couple of questions and then some questions in the book that will actually use a mirror formula that we'll discuss tomorrow. The math part of that's pretty straightforward, so that's why I left it for last. The drawing is definitely the harder conceptual stuff. Also for tomorrow, you've got a reading. Please submit that before class, because we'll start by talking with that and then go in through the math. If we were to need an extra day, we'll find some time to do that during our regular class time. But we'll be flexible with that. Okay. If there are no questions, then I will bid you adieu. Okay, have a good one.
You as well.